is chapter 1.1. We won't finish the entire notes today, but we will get a good part of the way through them. We probably could get through it, but we're going to take 2 days for it. Now, what we're talking about today is interval, set notation, and interval notation in sets. Now, well, sets and set builder notation. So we'll worry about set builder notation. We'll put the definition up here. But a set is a collection of objects. Today is, yep. So today's date is right above the whiteboard. They're not, but they will help you with learning the material and kind of internalizing it to where you can see it. So you can write it verbatim or write it in a way that you best understand it. So a set is a collection of objects. Braces are used to list the set's members. So this could be numbers or it could be letters. It could be anything, but it's just a list. Anybody else need a stapler? Thank you. Now, set builder notation is used to find a set of members according to its properties. The properties of its members. So 1, 2, 3, if I wanted to write this as a set, I would use a brace. 1, 2, 3, and a brace. So with any of this here is, I will tell you specifically if you need to get verbatim, but these, as long as you get the general idea, especially of what we cover today, is going to be good. Now, as we look at 1, 2, 3, well, it's easy to write that out. I can do my brace 1, 2, 3 and have another brace. That's fine. Now, when we look at the other example, the set of all odd whole numbers. Well, the first one would be 1, and then we have 3, 5, 7, 9, 11, 15, 17, 19, 21, 23, 25. Well, am I going to be able to list those out? Well, no, they continue on forever, yes? So writing it out like we do with 1, 2, 3 is not possible. It's not really possible to write a set like that. We can use ... but that's where we bring in set builder notation. So that's where set builder notation is going to come in handy because we can start classifying an entire group. So we can talk about all the odd, what they call whole numbers or positive numbers. We can list them out. So we can talk about bigger groups of numbers without having to physically write every single one of them as a set. So we'll get into set builder notation here in a minute. We're going to come back to it. But every set contains a subset. And a subset, sub, is a set that is a part of a larger set. So a subset is a set that is part of the bigger set. Or really what we say is when all the members of A are also B. For a group or a set to be considered a subset, it has to contain all the members, all the elements of the original set. So we'll do that here in a minute. When we look at this here, A and B, well, set A contains 1, 3, 15, 20, 27. Set B contains 1, 2, 3, 11, 15, 20, 27, and 100. Well, set A is a subset of set B because everything in A is included in B. So it is a subset. But can we say that B is a subset of A? No, because B has more than whatever A has. Now, can A be a subset of itself? Well, yes, A has, everything in A is also contained in A. A can be a subset of itself. Now, the way we would write this is that A is a subset of B. We could also say that A is a subset of A. Now, this is going above, but we could also say that A is a subset of this here. Now, a 0 with a line through it is not no solution. It's actually considered the empty set. It is the set that contains nothing. It is empty. Because every set, no matter what it is, will always contain the empty set. It's just defined in the sets. And that's getting into more of set theory. There's an entire branch of mathematics that's developed and pretty much focuses on purely on sets. Now, there's actually such thing as the set of the empty set. It's the set containing the set of the empty set. And I mean, we could keep going out indefinitely with that. Now, I didn't cover this with the previous hours, but I do find it interesting. You don't have to write this down. But when we talked in Algebra 1, so we talked about a number line, yes? Because y'all worked with number lines and doing inequalities, and yes? And this is what we call the real numbers. Because it contains all the real numbers, yes? Now, we also worked with graphs. So we got an XY coordinate plane. So this has 2 dimensions, yes? Yes, sir. Now, what we call in mathematics, we call this R, and we call this here R2. Because it's 2 dimensions. It's 2 parts of the real plane. Well, isn't everything that's contained in our number line, the real number system, a subset of the XY coordinate plane? Because that line, everything on the line, is contained in the XY coordinate plane. Yes? Because it's just the x-axis. Well, we don't live in just a 2-dimensional world. We live in a what? 3-dimensional world. And we call this R3. Well, the XY coordinate plane would be a subset of R3, the 3-dimensional plane. Well, by that statement, what can we say? That this is a subset of what? Well, we can't have a visualization of what really the 4th dimension is. We can consider it time because it's outside of our existence. But we could really continue this on to be a subset of Rn. For any dimension would be a subset of the previous one. That's subsets. That's just an interesting tidbit. We won't delve with that much at all, but that is part of subsets because it just contains of a greater set. Now, like Schedule was asking earlier, are we going to actually write these out? And yes, that's what we're going to do here. So I'm going to look at this here. So we have 4, 5. We want to write out every subset of this set. So what would be a subset of the set 4, 5? What has to contain in the set? Well, 4. What else could we have? And lastly, we could have 5, 4, or 4, 5. Because a subset is what? It contains, everything in the subset is contained in the set. So 4 is a subset because 4 is contained in the set 4, 5. 5 is a subset because the element 5 is contained in the set 4, 5. And 4, 5 is a subset because both 4 and 5 are contained in the set. Any questions on how we got the set 4, the set 5, and the set 4, 5 for our subsets? So what about CD? Okay, and CD. So we have 2 elements, 4 and 5, or C and D. We come up with 3 subsets. Any questions on this here? Okay. Well, now we're going to move on to, if we're good to move on, what about a set with 3 elements? Yes.
But can you switch it around or not?
It depends on how we want to classify it. Because if we want to say that the set 2, 4 and 4, 2 are unique to each other, then yes. But here, we're not going to distinguish that. We're going to say 2, 4, and 4, 2 are the same. Because that means for any one of these that appears, we're going to have to write it twice, which is just going to make the number of subsets even higher. Hey. So 2, 4. We also have 2, 6. Then we have 2, 4, 6. So we can go down the list because with 2, 2, 4, 2, 6. So we already have 4, 2, so we can do 4, 6. We already have 4, 6, and 6, 2, so we're done there. And then we have 2, 4, 6. I'll put this up here just to make sure. We have a total of 6. 1, 2, 3, 4, 5, 6. Should be 7. 1, 2, 3, 4, 5, 6, 7. So we have all 7. Because I have 1, 2, 3, 4, 5, 6, 7. How about 4? So we can kind of see that we'll have E, F, G, H. Because each one of the individuals would be a subset. EF, EG, EH. Now the order in which we do these really doesn't matter, but I do them this way progressively. That way I can know that I got all the subsets. Because if you haven't noticed yet, the number of subsets have been increasing at a faster and faster rate as we go along. So if I'm able to keep track, it makes it a little bit easier. Because then we can go FG, F, H, and the last set of 2 would be VH. There. Or GF. Yeah. Because we can use E and F again, but since we already have an element that's EF, FE. Oh, I get what you're saying. Flip them and do F first. Well, we'll consider FE and EF to be the same.
Well, I just didn't know as you went if you had to do all 4.
because we would do all four again if we considered those to be unique. So if we considered EF and FE to be two different things, then yes, then we would need all four. Now the next one we can have is EFG. Because now we can have groups of three. EFH. Yes. EGH. EFH, EGH. So EFG, EFH, EGH, because those are going to be different. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we got to 4 and we're up to 15, not including the, yep. Good luck today. Yes. So, any questions on this here? So it kind of makes sense. It's just a lot to keep track of. But these are all the different subsets that we could have. Now, what we're going to look at next is kind of talking about types of numbers. Now, we classify different groups. In mathematics, we gave different.
This is a reminder to the staff that we're doing a diaper shower for Casey and Bree Shaver in the high school office for the rest of this week. Thank you.
So, in mathematics, they grouped different numbers and gave them a name. Now, the first one is natural numbers. And natural numbers are naturally the numbers you count on your hands and your feet. 1, 2, 3, just our counting numbers. Now, mathematicians do have a tendency to be a little bit lazy. So this here, an N with 2 lines, is actually the symbol for the natural numbers. So whenever you see this symbol come up, what they're talking about is natural numbers. An N with 2 lines. Huh? It doesn't. It's infinite and continues on. Because 1, 2, 3, because the 3 little those dots is just saying it continues on in that pattern. So natural numbers we've covered, you've talked about before. All right. After that, we have something called the whole numbers. So on the next page. Can anybody see what the difference between the natural numbers and whole numbers is? Starts with 0. Yeah, it really just starts with 0. Now, the textbook gives whole numbers as a W with a second line. And this is the first time I've seen this used. Most upper-level math books don't talk about whole numbers. Because we're either going to talk about the natural numbers or integers. No. Natural numbers and integers symbol is a Z with the second line. So integers are our positive and negative numbers. We're not talking about decimals or fractions. It's just our positive and negative numbers. So this really adds subtraction to it that we can use because now we can actually have it be closed. So we can have positive and negative numbers. Those are called integers. And if we're going to reference whole numbers, 0 and greater, you would talk about, or they would say, the set of all non-negative integers, or the set of all integers greater than or equal to 0. So they don't use whole numbers much at all. We just talk about integers. And well, after integers comes rational numbers. Rational numbers. Whole.
Do we need to do that every time?
You don't have to. I'm just putting them back up there so that you can see them. Does anybody have a guess what the symbol for rational numbers would be? Exactly. It's a Q. Yep. Yeah. It probably has to come from the Greek or Latin roots, because most all mathematics, where we get it is from Greek, Latin, or Arabic. Those are a lot of the main powerhouses. And really, if you go into it, the Greeks were very advanced in a lot of their stuff, but a lot of it, they weren't as advanced as some. The Greeks and the Romans did not have the concept of zero. They just didn't have a concept for it, or a way to define it or describe it. Because you're essentially describing zero is a way to describe nothing. So you're putting description to nothing. So it's an interesting thing, and it wasn't until later on, the Babylonians, I think, were the first that got a base number system like our base 10, but they used base 60. A little more in depth. Now, after rational numbers, we get irrational. Now, irrational numbers that have a decimal point that is non-terminating and non-repeating. We cannot represent it as a fraction. We cannot represent it as a ratio. So our rational numbers are numbers that we can represent as a fraction, 0.25. So pi would be 0.26, going on and on and on. This is phi. Phi and e. These are three irrational numbers. So there's more to these than there are here. I mean, there's other irrational numbers that we could have. It's just the key with them is that there is a non-terminating, non-repeating decimal. So no matter how far we extend the decimal point out, we will never see it repeat. It will never end. Because 1/3 is 0.3 going on and on and on. We can represent it as a fraction. It is rational. Pi. No matter how we try to set it up with a numerator and denominator as a fraction, there's no way to actually get what pi actually is. It just keeps repeating on and on and on forever. So they're considered irrational. Now, I believe this is our I with two lines, but we don't normally reference it just like with whole numbers. Because if I'm going to include irrational numbers, because they're few and far between, we just talk about the real numbers. All of these here and everything you've worked with so far is the real numbers, the real number system. And that is where we get our R with two lines. So most likely when they finally got to rational numbers, well, real numbers had already been defined with our R with two lines. Today. Just let me know. All right. Can't charge you for it, but I can help you all out.
Wait, did you say you're going to charge?
I can't charge you.
We can slip a 10 in.
I mean, it's kind of a conflict of interest. Because, I mean, if the way that really works out, because I could intentionally teach poorly in here and then bring y'all all in and charge you for tutoring to go over it better later. But, all right, guys. What we're going to look at next is something that y'all have seen before. Intervals, bounded and unbounded. We covered these in Algebra 1, when we're talking about inequalities. Mhm. Now there's two main types. There's different ways that they can be set up, but there's two. We either have bounded, it has two endpoints, or unbounded, it has one endpoint. Yes. So our bounded intervals, so you have most of this down already, come in one of four different setups. Because we could have that A is less than or equal to X is less than or equal to B. Yep. So on the number line, it's pretty much saying that I have two endpoints that are included and everything in the middle. Or the second type we can have is A is less than X is less than B. So the two endpoints are not included, but we still have everything in the middle. And we also have that A is less than or equal to X is less than B. So again, one endpoint is included, the other is not, and we have everything in between. And the last one that we have is A is less than X is less than or equal to B. So A is not included, but B is. Now the second column is interval notation. So brackets are used to define or say that the endpoints are included, and parentheses are used to say that the endpoints are not included. And I included the graphs out to the side just so you can kind of see how they would look graphically. Now, the reason we use A and B is to define any point, any value for A and B. So you can put those in if you need or want. So these are the four that we have. Now A, the value on the left, the values for A will always be less than the values for B, because the smaller value goes on the left, the bigger value goes on the right. I have been to several.
Well, I mean, I see them, but okay. I like baseball, but I haven't watched the Rangers play or whatever.
Yeah. Oh, I got all those off of eBay. Those little pennants they gave out when they actually hung the banners for each one of those as a little game freebie. I live too far away to go to that, and I can't get as good as tickets as I did when I was in college. So, all right, guys. Unbounded intervals. So these are the ones that have one endpoint and go off indefinitely. Now there's four main types that we can write as inequalities. And then the last one is really considered all real numbers if we have the whole line. So the three or four that we have is that X is less than or greater than or equal to A. X is greater than A. X is less than or equal to A, or X is less than A, are the four kind of unbounded intervals that we could have, because one side is unbounded. It continues on indefinitely in one direction. So for our interval notation, we'd have a bracket A comma infinity for the first one, A comma infinity with parentheses. We'd have negative infinity comma A, the bracket. Well, you can always turn the paper sideways and draw an 8. Now, does anybody know why we use parentheses around infinity and negative infinity? Because we can't contain it. We can never get to it. There's a kind of experiment kind of riddle that they work with dealing with infinities. It's called the infinite hotel. So if you think about a hotel that has infinite number of rooms, massive hotel, infinite number of rooms, pretty much. So in that hotel, there's infinite number of rooms and all of them are full. a person comes in at wanting to get a room. So to fit them in, they ask the person in room 1 to move to room 2, the person in 2 to move to 3, 3 to 4, 4 to 5. Everybody moves down 1 room. So now everybody has moved down 1 room, and now room 1 is open. So we just created a bigger infinity. And that's one of the reasons so we can never get to it, because again, we had infinity. We moved everybody down 1. Now we made an opening space, so 1 more person can fit in. So now the infinity is bigger. No. So, but you can hear it later. Any questions on this here? Okay. So what we're going to do first is we're going to write each interval in interval notation. We're going to write each one of these in interval notation. So the first one we have is -2 is less than or equal to x is less than or equal to 3. So what would our two numbers be?
-2.
And which one goes on the left? And we would use brackets because both are included. Because it says less than or equal to, so both numbers would be included. Smaller number goes on the left, bigger number goes on the right. So the next one we have, are there any other questions or any questions on A before we move on to B? You all remember doing this in Algebra 1? Kinda. So what would we do for this one here?
Make it infinite. And doesn't it make it an infinite?
That is a good thing. You can just do it yourself.
Since x is greater than -1, the smallest value we could have possibly would be -1. Now, since it's not included, it's not equal to, we do put a parenthesis. Yep. And we put another parenthesis. Any questions on B? Okay, let's look at C.
Oh, so now we have to find out what it is by looking at it.
Yep,
Oh, I have it.
-3 and 4.
How do you know the sign? Oh, we're just gonna
So there would be a parenthesis, guys. Huh?
Do the or like 3 is less than or greater than 4. I thought we were trying to find that out.
Not yet, not on this one. But we do have, exactly, we do have a parenthesis and a bracket, which goes where? Almost, because is -3 included? If it's filled in, it is included. If it's open, it is not. So we fill in the circle or the point when it is included. We leave an open circle when it is not included.
So on the next one, is it like what if it's arrow? Do you just
The two arrows would be -infinity to infinity because it's all real numbers. Yes, so this would be -infinity because it extends out indefinitely towards the negatives. And the biggest number is 3. Yes. Any questions on any of these here? We good with these here? Okay. So have you copy this down here? Because now we're going to get back to set builder notation.
what time do we get out here?
At 132, 129.
All these X's, why would you put letters in math?
To define any type of situation that could occur.
I wouldn't.
What shows you?
Hmm?
What shows you?